So hi everyone, I'm Pietro, and today Enrico and I were going to present our latest work on bypassing Spectre hardware defenses to leak kernel data. So first of all, some credits to the people behind this project. As you can see here, it's me and Enrico, and with us, Marius, Herbert, and Cristiano, that are part of our VUSA group in Amsterdam, helped us a lot in this project. So what is this project about? This project is about Spectre, which is a vulnerability that affects most modern CPUs. And one of the reasons why Spectre was considered interesting from the beginning was that it allowed attackers to leak data even across privilege levels. So for instance, you could build exploits leaking data from the kernel to user space, and this would completely disregard the concept of supervisor domains. So what CPU vendors did when this vulnerability was discovered was to release all sorts of software and hardware defenses. And for the purpose of this work, we've mostly focused on the defenses trying to thwart these kind of cross-privilege exploits. And the question we asked ourselves was, do these mitigation actually work? And little spoiler, no, they don't quite work as intended, but we're going to get there in a bit. So how do we split this work? I'm going to start with a presentation talking about Spectre and a bit of background on how it works. And then I will talk about these defenses that they released and also how to bypass them. And afterwards, Enrico will pick it up and we'll talk about our new primitive, which is branch history injection. And then it will talk about how we can exploit this, and we'll give also a live demo. So hopefully that's going to go well. So let's start with Spectre. What is Spectre? Spectre, as I said, it's a vulnerability that affects most modern CPUs. And in particular, it affects a specific component inside the CPU, which is the branch prediction unit. And the branch prediction unit, as the name suggests, is simply trying to predict the execution of different branches. So for instance, in this case, here we have an example of a conditional branch that is trying to perform a bound check for an array. And what happens here is based on the value you provide of the index of the array, you will figure out, you will start building confidence at the BPU level to know if the branch is usually taken or not. So if usually the X value is within the boundaries. So for instance, in this case, if you provide 0 as a value, the BPU will start building confidence. OK, this is a value within the boundaries, so I should take this branch. Same with 1 and 2 as well. Now what happens is, if you provide a value outside the boundaries of this array, and the BPU built enough confidence that this branch is usually taken, it won't care that this read shouldn't happen. It will do it anyway, speculatively. So speculatively, you can perform an out-of-bound read. Now, clearly, this is not a big deal in the architectural domain, because eventually you will figure out, OK, this shouldn't have happened, so I will just squash this read. Never happened. I'm going to move on to whatever I need to do when the read is out of bound. But speculatively, you still perform the read. And what happens when you combine it with another sort of microarchitectural attack, like a flash reload, which is a cache attack? So what you can do is, for instance, combine this out-of-bound read with a dependent out-of-bound read. So what we'll do is, for instance, if in the location 256 you have the value 3, what you can do is perform a second read based on this value on a second array, which is your flash reload buffer. And this value, this read will cache the value of this reload buffer, so that entry of the reload buffer will be cached now. So afterwards, what you can do is to leak secret data. You simply time the memory access of this array. And eventually, you will time the whole array, and you figure out that the fast one was the one you actually leaked. And this allows you to leak this data that was out of bound before. And this doesn't only work in the case of conditional branches, but also in the case of indirect branches. So for instance, here we are going to use an example of polymorphism to explain how indirect branch prediction works. In this case, here you have two classes, a cat class and a dog class. And both of them implement the speak method. And when you call the speak method from the cat class, you would expect the function to execute the meow function. And when you come from the dog class, you would expect the woof function. And what happens here is the BPU can also help in predicting the execution of these branches. So when you call the function from the cat class, in this case, the BPU needs to figure out where to jump. And to do so, inside the BPU, you have you have a table, like you have a specific cache called the branch target buffer, or BTB, which contains a different target for all the possible functions that you recently executed. And in this case, you have two options, clearly. For this function, you have two targets. One is meow and one woof. And if you're coming from the cat class, in this case, meow will be a correct prediction, so you will speed up the execution. And woof will be a misprediction, which means you will execute that function speculatively, revert back, and then execute the meow function afterwards. What's the problem with this? The problem is you can exploit Spectre. You can build a different variant of Spectre, which is known as Spectre v2, that attack this kind of indirect branches. And the reason why you can exploit this is because the branch target buffer is a shared resource across different contexts on the CPU. And what an attacker can do is simply overwrite entries in the branch target buffer with more interesting targets, like a function like leak secret. And leak secret would be something like the one we discussed earlier of a flash reload attack. So now what happens is when the cat class will call again the speak function, at this point, for that specific class, you would expect to execute the meow function, but now you overwrote it with the leak secret function, which means that you will execute the leak secret function instead of the meow function. And as we said, this works across different privilege levels, so you can build cross-privilege attacks. And this you can do it across different applications running on the same core. You can do it between user and kernel, and even guest and host, because the CPU has no idea that there are different contexts. So you can imagine this is quite scary, right? Because this allows you to build attack across all different privilege levels. So what do we do next? What the CPU vendors did when this was discovered was come up with all sorts of defenses. And they started initially with software defenses, because it's faster to implement. And the first one was known as red polling. And red polling, what simply does is convert all the indirect calls like for instance, this call area X we have here, with this big blob of instructions that the general idea behind it is just trying to stop speculation altogether. So instead of performing an indirect jump, you will convert this to this chunk of code, which will not allow you to perform any speculation on this. So you cannot exploit Spectre anymore on this. AMD did something very similar. It's called AMD red polling or LFence jump. And this is basically the same exact concept, just a very different implementation for a different microarchitecture. Whereas ARM, because of the fragmented ecosystem of different architecture they have, they do very weird things depending on their different systems. And in hardware, both Intel and ARM worked on two different mitigation known as EIBRS and CSV2. And this mitigation, even though they're very different in implementation, we guess, they're actually very similar in concept. And the idea behind them is that you want to enforce predictor mode isolation directly in hardware. And what do we mean by that? The general idea is that we want to tag the BTB entries by security domain. So the way you can visualize this is you can simply extend the BTB with an extra column where you tag the entry with the other user or kernel context or guest or host or whatever. And afterwards, what happens is when you perform a jump from the kernel context, for instance, at this point, the PPU will allow you only to speculate to targets that belong to the kernel context. And as a result, you can look at this as basically implementing SMAP, but in the speculative domain. So here you cannot implement any more attacks that jump back to user-defined functions. So the question we asked when we started with this project was, is this isolation complete? And the first thing we did was going to look at their manuals. And this is the ARM manual for the CSV2 function. And in their manual already, they suggest that an attacker can exploitatively control speculative execution only in hard-to-determine ways. So clearly, we're kind of confused when we started working on this, because what does this even mean? So we started looking at how we can bypass these mitigations. And now I'm going to explain to you how we did this. And to do so, I'm going to start again with our example of the cat and dog. And I'm going to explain a bit more about how indirect branch prediction works on the CPU. So as we said, here we expect the cat class to execute the meow function and the dog class to execute the woof function, right? But from the BPU side, both functions come from the same method. So the speak method will need to execute both of them. So here you have one single function call, right? So how does the BPU distinguish the two different contexts? And the answer is exactly this. The prediction needs to depend on the context of the function call. And what do we mean by that? With context, we simply mean the history of previously executed functions. So for instance, in this case, if you're coming from the cat class, you can expect that the previously executed functions or if condition would be something like a breedCat class function that follows with a new cat and kitten for sword. And this is basically the context that allows you to distinguish which one of the two is the one you're coming from. So at this point, you can use this context to generate the tag for the BTB. And here you will have, you can see that since the context is very cat-related, you're supposed to speculate then to the meow function. And how does this work in hardware? In hardware, you can implement this in very different ways, but one of the many variants that was discussed in the past is to use both the call site and the context to compute the tag. And what they suggest is that they hash together all the different jump addresses of the context into a shift register. So you can just like squash all this information inside a single shift register. And afterwards, you combine this value with the actual call site of the speak function. What you do is, again, like you get the value of the shift register, the call site, another hash function, and you compute the tag. Now, as you can see here, we have our breedCat context, and as a result, since the context is very cat-dependent, you will need to speculate to the meow function. So this, you can see that like, the history heavily depends on the context. But how does it work when you perform a mode switch? So a mode switch between user and kernel space. Our intuition is that the user history is necessary for accurate kernel prediction, right? And I'm going to use this example of a syscall to explain why this is the case. So for instance, in this case, we're trying to perform a printf. And when you perform a printf, what you want to do is a syscall, and you want to execute a syscall write to write out the context, the data to standard out. And what we'll do is generate a tag based on this whole history shared. And this will store a new entry in the BTB for a syscall write. Afterwards, when you perform a different function, for instance, get char, at this point you want to perform a second syscall, which is syscall read. And this is supposed to store another entry in the BTB, right? But in this case, it would be for the syscall read. And our general intuition was exactly this, that like, if the history doesn't depend on the user space context, it would be very difficult to understand to which syscall you need to jump to, because the syscall, the kernel entry point is always exactly the same, and you simply have a dispatcher to different syscall handlers. So this means that if this mitigation don't take into account also the history of the user space, all the misprediction will be very slow. So in our case, we expect that the next time you call a printf, the BPU will think, OK, I already seen this user history, so I need to speculate to syscall write. And we tested this with an attacker mindset, and we thought, then, can we control kernel branch prediction using only user space history? So we went back to our example of the syscall read and syscall write, but in this case with the two generic syscalls and two generic contexts. So what we did was we generated a jump chain in user space that we call context A, and we followed this with a syscall that is called syscall A. And this will generate the entry in the BTB to speculate to syscall A. And afterwards, we do the same for context B and syscall B. So two entries in the BTB for syscall A and syscall B. And finally, we just mix and match the two. So we would have a context A, but then we follow this with syscall B. So as you can see here, the history is syscall A, but then eventually you actually want to perform syscall B. And this experiment can tell you if our intuition was correct. And indeed, we tested this, and when you perform this history of context A followed by syscall B, what you observe is that it speculates to syscall A. So the speculation is based on the context. And the reason is, again, because the BPU will think, I already seen this user history, so I should speculate to syscall A. Now, this is wrong, clearly, because you want to speculate to syscall B. But that's not a problem, because eventually you execute again syscall B, so that's not a big deal. And we tested this on most modern Intel, ARM, and AMD CPUs. On AMD, clearly it didn't work, because they still rely on software defenses like red polling that completely stop speculation. But on all the Intel and ARM CPUs that we tested, we could observe perfect misprediction in this experiment. So let's just try to understand what this means. With this experiment, we basically show that the user context can be used to mistrain kernel indirect branches, even in the presence of these new hardware defenses. And this is our new primitive that we call branch history injection. And now Enrico is going to explain to you how we can use this to build a newer exploit. All yours.
OK, thanks, Pietro. So as just Pietro said, we have a very simple primitive right now. We can control the branch prediction process of the kernel from user space injecting some history. But as you can imagine, we are still far away from building a full exploit. And to reach that point, we need to answer two questions. The first one is which target we can speculatively execute. And by that, I mean, OK, we can mispredict this indirect branch in the kernel, but where we can speculatively execute. And similarly, we need to answer the opposite question. OK, there are many indirect branches in the kernel. Which one we can mispredict? And for doing so, you have to perform the reverse engineering of the branch prediction unit, so the silicon inside of the CPU. And usually, a first step is to have a look at the patents that you can find online. However, we were quite unlucky on this aspect, so we didn't find anything useful. So we started doing the, let's say, classical reverse engineering of the hardware. And you can do this by simply performing some specific instructions, some experiment, and observing the performance of the CPU depending on your input of the experiment. We started very well, finding some nice pattern in the hardware. But eventually, we failed, mainly because the hardware is becoming so complex that reversing them is very difficult. So after 2 months, we decided to stop this approach because it was very hard to understand the details of the branch prediction unit. So again, we failed with these two approaches. What is left? Our good old friend, brute force. Let's make a small step back to understand why the brute force approach here works. So again, as an attacker, we only control the history. Okay, this is the only, let's say, injection point we have. And if you look back at a possible implementation of a branch prediction unit, we only control the parts that are highlighted in the red, so the history, or basically the content of the branch history buffer, that is this register containing a snapshot of the recent execution. So what if we randomize these bits and let's see what happens? To do so, we can build a very simple experiment. So as you can see here on the left, we have a jump chain that is a simple trick for us to generate an history. So you can see from the address lead cafe, we are jumping to that beef, from that beef to Dudukak, and so on. Here the idea is that we are generating a specific history. And after this, we are going to an indirect branch that will always land to target A. The idea here is to associate history A with target A. So every time the branch prediction unit will see history A, it will say, ha, it's a good idea to jump to target A. So then we generate a random history, that is history B. And again, this history should always jump to target B. So as you can see here, our goal was to associate target A with history A and target B with history B. And if we execute these two code paths in an alternate fashion, we observe an always correct prediction from the BPU. And this is expected because we are giving, let's say, the golden scenario to the branch prediction unit to perform accurate prediction. But what if we keep the left code path constant and we randomize the right one? Eventually, what we observed was a 100% misprediction rate. So in other words, in the silicon, in the CPU, the branch prediction unit wasn't unable to distinguish history A from history B. So you can clearly see the values are different. But since they are hashed in a single register, they will collide to the same value. And from the perspective of the CPU, they are identical. So that's why it's always performing this prediction. And for us, as an attacker, this is perfect, because just by controlling history B, we can accurately perform misprediction to the target we want. And let's do a small last experiment. Let's completely separate the two code paths, so we don't have anymore a single indirect branch. We have two of them. And as you can see, from history A, we always jump to target A, history B, target B. And here also, surprisingly, by randomizing the history B, we even managed to find a case of speculation from the indirect branch B to target A. If you think about this, is very weird because that code path never jumped to target A. So this proved actually that the branch prediction unit wasn't able not only to distinguish history A from history B, but wasn't even able to distinguish the different call sites. And this, as an attacker, is an amazing primitive, because now you can mispredict any indirect branch and speculate whenever you want. It's like total freedom to do whatever you want. And now you may ask, OK, brute force approach, easy, but probably is going to be super slow, right? Well, not really. For us, we're very lucky. It was very fast to perform the brute force approach. Maybe just to give you some number. So you can see here, this is for the Intel 10 Gen. If you try 40,000 times, you are almost sure to find this colliding history to do the misprediction that you want. And we tried also on many other architectures, and as you can see, the entropy is very small. I mean, the maximum was 17 bits that you can break in less than 1 minute, and a few seconds are enough usually. OK, let's make a small recap to understand what is our primitive now. So our goal is to mispredict an indirect branch in the kernel. And let's say this indirect branch in the kernel architecturally can only jump to 2 valid targets, target A and target B. And again, we are considering system with hardware defenses, so we can no longer speculate on user-provided function. As an attacker, we have very limited control, just the previous instruction before the Cisco instruction. So we control only the history before performing the mode switch from user to kernel space. And as we demonstrated on Intel and ARM CPUs, you can speculate to the valid targets in a very precise way, again, just by controlling the history. But the best comes for Intel processor, where you can actually speculate wherever you want. And this was quite powerful because you really enlarge your attack surface. And to give you some numbers, in the Intel 11 Gen, for example, the context or the history is composed by the latest 67 taken branches. And as an attacker, we only need to control 8 of them. So we can even attack very deep-nested indirect branch in the kernel. OK, let's switch to exploitation. So we have our nice primitive. How can we do something interesting with it? To show the main idea, let's have a look at an attack plan. So the first step is to ensure that our gadget or our code we want to execute in the transient domain is present in the branch target buffer. And for doing so, you just need to execute that function code and ensure the BTB is fit with the value we want to speculate on. Then later, we do what we saw before. Simply, we generate a random history. We perform a syscall. Any syscall will be fine. And then what happens? As soon as we enter the kernel space, the branch prediction unit will say, oh, I don't know where I should jump. Let's have a look at the recent execution, so the history from the user space. We'll generate a tag. And let's say the first time we are unlucky, the tag is not the one we want. No problem. We are going to jump to get PID. No problem. We can repeat the process until we win. So we ensure again the leak gadget is in the BTB. We randomize the history again. Another tag will be computed, and so on, until eventually we are lucky. We break the let's say the entropy, and we generate this exact same BTB tag. And this will basically allow us to speculate on the function we wanted to. OK, now you may ask, but why we're always talking about this syscall table handler? I mean, there are many indirect branches in the kernel. Why we are so focused on that one? Well, the main reason is that you can very easily execute that indirect branch. Any syscall will trigger it. But actually, the best part of it is that the first argument of this syscall table handler is that is pointing to all the user space saved register. So as an attacker, we have a lot of control of the memory and the register that we can use for finding a Spectre gadget. Then the biggest challenge is to find a gadget. So as you can imagine, the kernel binary is huge, so finding the few instructions we need to leave at rest in the cache is you should be able to find it. It's a very tedious work. It requires a lot of time. So since we use a brute force approach, why we should also here choose the lazy way, you know? So at the time where we were doing the project, there was this nice feature named unprivileged eBPF that, in a nutshell, for us is a JIT engine in the kernel that unprivileged user can use. Yeah, it's a bit strange. I mean, you can literally JIT code in the kernel from an unprivileged user. And for us, this is amazing because you just need to find the correct BPF opcode to JIT in the kernel the perfect leak gadget directly in the kernel. So this was very helpful for us. But now you may ask, but wait a second, so the kernel developer allowed you to inject Spectre gadget in the kernel? I mean, this sounds unsafe. I mean, for sure they have proposed some mitigation against this. That's correct. eBPF is full of mitigation against Spectre, but on variant 1. And now you'll see why. So eBPF, again, is just a tool where you can write some, let's say, packet filter for incoming packets. And architecturally is doing something very safe. So whenever we receive a packet, we are accessing, for example, the mark attribute. And depending on that attribute, we are accessing another array. Everything is inbound, and even in the speculative domain, there is no exploitation possible. Over here, thanks to the variant 2 of Spectre, we are no more coming from the eBPF dispatcher. We are coming from the Cisco handler. So now, there is no more packet. Literally, there is a transient type confusion going on. And we are not accessing the mark attribute, but we are dereferencing the register 12. So literally, we are dereferencing arbitrary memory address in the kernel, and then leaving a trace in the cache that later we can use to recover the leaked data. And here inside is that transient type confusion, or basically Spectre Variant 2, really helps you to bypass Spectre mitigation. One last missing component is that we need a precise timer to distinguish cache hit or cache miss. And again, our beloved friend eBPF is so kind to provide it to us. So yeah, we have everything to build our exploit now. And let's try a live demo. So you can imagine running micro-architectural attacks live is not a good idea, but we're going to try anyway. So here I'm connected to a machine that is vulnerable, that is an Intel 10th-gen CPU. And as you can see, we have an updated kernel. And if we check the mitigation, we can see is vulnerable because we have an updated system. They are aware of this attack. So we start by building an eviction set to ensure that the branch prediction unit will give us a larger speculative window. And after this is complete, oh wow, it was very fast. So we are trying to find the colliding history. You see 0 seconds required. And now we are already leaking kernel memory. So the first step is to break SLR because we need to read only a meaningful part of the kernel. And now we are already linearly sweeping the kernel memory, looking for something interesting. And here we decided to look for the etc shadow root password. Usually take a moment and let's see. OK, here we are. So you can see in 30 seconds, nice. And to prove is actually the correct password, as root, let's print it, and it matches perfectly. Nice. OK, nice. First time. OK, let's quickly conclude with the vendor response and mitigation. There are many affected CPUs, but to summarize, every Intel CPU starting from the 10th gen is affected. So any new CPU from Intel is affected. And regarding ARM, it's a bit more complicated, but in a nutshell, every, let's say, CPU from the latest 2 years with a branch prediction unit should be affected. What about the mitigation proposed by the vendors? So Intel proposed mainly one single defense, that is to disable unprivileged eBPF. That is this JIT engine in the kernel. If you think about is not an ideal solution because you are removing a nice tool for its exploitation, but the bug is still there and is not going to disappear soon. They are promising also some software and hardware mitigation that are mainly doing the same thing. On a mod switch, for example, from user to kernel, they are clearing this branch history buffer so that during the prediction process, the user history is no more used in the prediction process. And ARM did exactly the same, slightly different, again, software and hardware mitigation with the goal of clearing this branch history buffer. And AMD, as we said from the beginning, is not affected because they are still relying on a software mitigation. So let's say by keeping a software mitigation, they are safe by not choosing a faster and hardware mitigation. Well, actually, the same day we released our paper, Intel proved that the AMD defense was broken. So a few months ago, at the same time, Intel, ARM, and AMD were still affected by Spectre Variant 2. 3 years later, the discovery of it, and yeah, was not that great. To conclude, together we saw that the attack surface of these attacks is too wide to define. It's very difficult, even for us and the CPU manufacturer, to guarantee you are safe against this threat. And we do believe that we need more principled defenses because even after our attack, they release stopgap defenses. Like disabling eBPF, yeah, it's a good idea, but the bug is still there. Maybe someday another researcher will find another gadget, and we are starting from zero again. But to conclude on a positive note, during this project, we really noticed how it's becoming harder to build such exploit. And we can make a comparison with software exploitation. 20 years ago, writing a buffer overflow exploit, I guess, was much easier. Today, with ASLR, canaries, and so on, it's becoming way harder. That was our talk, a little dirt history. Here you can find our project page. If you want more details, we have the paper and also the source code for the exploit you just saw.